Okay, so today in section 9.3, we're going to look at graphing rational functions. Now in 9.2, we did graph, but we only graphed when we could use those specific parent functions of some number over x. In 9.3, we're just kind of talking about, in general, any rational function, not necessarily something that follows a parent function mentality. Now, what we're going to do today in this podcast is we're just going to look at all of the little details. Now, in practice 9.3, we're going to do a few in class. We'll actually go through and graph the whole thing. So today we're just kind of looking at some of the different parts, and then we'll kind of put those together to graph. I may ask you, I probably will ask you to find the parts without a calculator. If I ask you to graph the whole thing, I will let you use a calculator unless we're doing parent functions. All right, so a lot of definitions here, so you may need to pause and write things down. If you need to do that, feel free to. So first of all, if we're talking about a rational function, it just means that it's in fractional form. It's a fraction. We already have talked about asymptotes this year, but remember, an asymptote is a vertical, horizontal, or slant. We're going to have a slant, which means it's just at an angle, line that the graph approaches but never reaches. So we've had a lot of vertical asymptotes before, and so the graph approaches it but never actually gets there. Same thing if it's horizontal or slant. Now, when we're talking about asymptotes, horizontals are a little bit weird. I'm going to put a horizontal asymptote on there. So there's my horizontal asymptote. Sometimes you'll have a graph that does something like this. See how it approaches here? It behaves like an asymptote, but it actually crosses over on the other side, kind of like it's half asymptote, half not. That can only happen with horizontal ones. Verticals and slants will never be crossed, not have this kind of weird thing going on. But that does sometimes happen with horizontal asymptotes, so just a heads up on that. Okay, so here's what you need to find when you're graphing. You need to find asymptotes and holes. We're going to talk about that part today. And then you'll also need to find points to fill in your graph off of your calculator. We're going to do that as we practice on some of these tomorrow. Today we're just doing the details. So what I'm going to go through and do is I'm going to give you sort of the rules, because this is pretty memorization heavy. I'm going to give you the rules for horizontal asymptotes, then slant, then vertical. So let's start with horizontal. Remember, you may need to pause this to write things down, so feel free to do that if you need to. All right, so horizontal asymptotes, there's basically three different situations. And I'm just going to go to the next slide and pull up a problem and then come back to this. So here's what you're going to do. This is like an x to the first. You're going to compare the exponents in the top of the fraction, biggest exponent in the top of the fraction and the bottom of the fraction, and you're going to compare those, and based on that you're going to come up with using one of the three rules on the previous slide. So like here the bottom's bigger, denominator's bigger, here they're the same, here the top's bigger, meaning the exponent's bigger in the top. Basically you've got three rules here. If your denominator has the highest exponent, there's no horizontal asymptote. If your denominator has the biggest exponent, then y equals 0 is the asymptote, or the x-axis. They're the same thing. If the highest exponent's the same, then you're going to go through and make a fraction using your leading coefficient. Let's see if I can write coefficient from the numerator divided by your leading coefficient from the denominator. Okay, so let me show you what I mean here. So if you're looking at this one right here, your denominator is bigger. So if my denominator is bigger, I would use this right here. So my asymptote is y equals 0 or the x-axis. Now here's what that means. My horizontal asymptote would go right here. At y equals 0, it's the same thing as the x-axis. So that's where my horizontal asymptote would be. All right, second one, they're the same. So if they're the same, I'm going to make a fraction out of the leading coefficients. So 4 over 2, which is 2. So my asymptote is at y equals 2. So my asymptote then would be right here. Okay, and in the third one, the top's bigger. I have the 3 versus the 2, so the numerator's bigger. In that situation, no horizontal asymptote. Now I'm going to always abbreviate horizontal asymptote as HA, horizontal asymptote. Feel free to do that. I know what you mean if you do that. Okay, so that's horizontal asymptotes, straight up memorization pretty much. The second kind of asymptotes we're going to look at is slant asymptotes. That just means that the asymptote is at an angle. It's a line written in y equals mx plus b form. Okay, so here is your situation. You will only have a slant asymptote when the graph of the rational function, I'm wording this differently, you'll have a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So the numerator is 1 more than the degree of the denominator. Looking at the problems we just did, this one right here is when you'd have a slant asymptote. Now I want you to notice this. When you have a slant asymptote, you do not have a horizontal. It's a situation when you don't have a horizontal. So you will never have both a slant and a horizontal asymptote. You'll have one or the other, maybe neither, but you won't have both. Okay, now see how the top's 1 bigger than the denominator. You're looking at those biggest exponents. So here's how you're going to find your slant asymptote. You're going to do division. Divide the bottom into the top. I'm going to do synthetic division here, mainly because I can. So 1, -4, -5. And let me do my synthetic division quickly. So my answer is x plus 1 and -2 over x minus 3. Okay, so here's the deal with slant asymptotes. Your remainder does not matter. You can mark it out. The rest of it, put a y equals in front of it, that's your slant asymptote. Now I want you to notice this is in y equals mx plus b form. I'm going to graph my slant asymptote on here. So I've got a y-intercept of 1 and a slope also of 1. So I'll go up 1, over 1, up 1, over 1. There's my slant asymptote. Okay, so I'm going to do synthetic division, disregard the remainder. The other part is my slant asymptote. Okay, so let's do that here. Okay, so my remainder doesn't matter, so I'm going to go ahead and mark it out. And then 2x minus 1 is my slant asymptote. Okay, and I'm going to graph that. So y-intercept of -1, a slope of 2. So there's my slant asymptote. Okay, our last kind of asymptote that we'll have is a vertical, which we've had before. To find your vertical, you set your denominator equal to 0 and solve. So right here, I'd set my x minus 3 equal to 0 and solve. X equals 3 is my vertical asymptote, which means right here at 3. That's my vertical asymptote. Okay, just a heads up on this, you may need to factor if you've got a messier denominator. I'm going to factor this x minus 1, x plus 1, which means when I set those equal to 0 and solve, x equals 1 and x equals negative 1, those are my two vertical asymptotes. So at 1 and at negative 1. Okay, now I have the same denominator here, but I want y'all to see something, so I'm going to go ahead and factor this again. A second ago, I had it already factored, the x squared minus 1, x minus 1, x plus 1, which means my vertical asymptotes would be at 1 and negative 1. Now, I want y'all to notice something about this problem, though. See how my x plus 1s would cancel out? If that happens, this isn't a vertical asymptote anymore. It's called a hole. We're going to talk more tomorrow or in practice 9.3 when we graph. We're going to look a little bit more at what the hole looks like on a graph, but you're going to have a hole whenever one of the terms cancels out. Whatever its vertical asymptote would be becomes a hole. Now the other one is still a vertical asymptote. So in this problem, I only have one vertical asymptote at 1. Negative 1 is a hole, which just means it's going to be a little hole in the graph. You'll see more what that looks like tomorrow. So last thing, let me let you get a definition of hole. A hole occurs when one of the factors in the denominator cancels out. Like we had a second ago, it's no longer a vertical asymptote, but a hole, simply a break in the graph. Okay, so I'm going to do one more of them. Pause this if you need to write it down. So I'm going to go ahead and factor my x squared minus 4. So I'll have x minus 2x plus 2. Now before I cancel, that means when I set it equal to 0 and solve, I would get 2 and negative 2. Now, since the x plus 2's cancel, this is a hole, which means it's a break in the graph, but not an asymptote. This is still a vertical asymptote because it did not cancel out. So my only vertical asymptote then is at 2. All right, so this is 9.3. Remember, we are going to finish up tomorrow with actually graphing some of these versus just finding all the little details. So keep that in mind. I may have given you one or two on the homework to try graphing the whole thing, but we are going to come back and do that some tomorrow. All right, so this is 9.3.